Hey folks, I wanted to go through a few more details about writing exponential equations. In the first examples, we'll just assume that these are exponential, but at the very end, we'll have an example where maybe it's not quite so clear, even looking at the numbers in the table if it's exponential. So we'll have to dig a little bit deeper on that. So here's essentially the process we can use throughout. We looked earlier in previous class lessons that any table that's exponential has infinitely many different equations we could write. So we're just going to follow one standard procedure to find the one that might be just a simple process to follow. And it's going to be based on the top row of our table, regardless of what this input value is. The top row of our table we will always think of as the starting number. And so we have essentially a starting number of 5. And then because this is an exponential table, we move down the table with a multiplication pattern. In this case, the multiplier is times 2. So I'll be using this common language throughout of the starting number, meaning the starting output value of the function, and the multiplier, which later we'll give a new name to, but the multiplier is the number that we multiply down the table to get from term to term to term. And so in this case, we're looking for essentially an expression that represents what to do for any input. This is essentially our equation. And we're going to basically start it just like we generated these numbers by starting with our multiplier and then multiplying repeatedly by the number of 2. So the number 2 we'll put inside parentheses and we'll use an exponent to represent the number of times we multiply by 2 to get to our desired location. So for instance, if I wanted to know what the output value was when x is 10, since we started at 0 and 5, we would have to double 10 times. So this value would be our starting number times our multiplier raised to the 10th power. And we can generalize that to say, therefore, for any number, input x, we would have to start with our starting number and multiply by our multiplier x times. So we'll have this as our equation for this number pattern. Now what we're going to do on the next couple of pages is actually look at the exact same number pattern, but just imagine that it starts somewhere different. So notice how the numbers are the same. We've got 1 and 10, 2, 20, 3 and 40, and it keeps doubling. But just as a comparison for ourselves, we're going to now think of this as the starting number. So now we start with 10 before we begin this process of repeatedly multiplying by 2 to move down the table. The numbers are the same, but because the table is organized differently, we're going to end up with a different expression and a different looking equation, but it's equivalent to the other one. All right, so in this case here, if we wanted to find the number that goes with x equals 10, we could start with our starting number, multiply repeatedly by 2, but unlike the last example, I don't need to multiply by 2 10 times because I'm already starting on row 1. And remember, before row 1 was where we were after we already doubled once. So instead of needing to double 10 times, since I'm starting lower, I actually only need to double 9 times. One way that someone pointed out is to think of this starting input value as the number of doubles or multipliers that have already occurred. We've already got 1, so to get to 10, we only need 9 more. And that means our expression here will change to our starting number times our multiplier raised, we want 1 less than x. So an equation for this table, which is the same table as before, could also be expressed this way based on a new starting number and changing the number of times we need to use the multiplier. Let's compare this one more time with the exact same table. 5 and 160 are the same numbers from the other two tables, and I've just extended it downward. So now we'll think of this row and 160 as our starting number. And it's still, still the case that we multiply by 2 to move down the table. So in this case, we have our input value x using starting number 160, our multiplier, and think of it as we've already had all of the doubles starting from 0, 1, 2, 3, 4, 5. We've already doubled 5 times. So we need to do 5 less doubles to get to x. Since we've already started, think of it kind of like a head start or a boost. So this equation could also be written 160 times 2 raised to the x minus 5 power. The same table, 3 different representations, 3 different equations, all consistent, all equivalent. So let's move on and look at 2 new examples. These are new tables with new numbers, different values in the y column, and let's use this consistent process. The top row gives us our starting number. This case is not a doubling pattern. It looks like it's multiplying by 3. That seems to be consistent all the way down. And so let's represent our expression for input value x as our starting number times our multiplier raised. And in this case, since we're starting with input value 0, we need to double as many times as matches the input value. Over here, we're actually seeing a decreasing table of numbers, but we'll still think of the top row as our starting number. And in this case, even though we might think of it as a division pattern, because our process is built on the operation of multiplication, I'm going to have to think about representing this division process as multiplying. So dividing by 2 is the same as multiplying by 1/2 or 0.5. That's consistent, times half, times half, times half. And so we can represent this decreasing exponential pattern in the same way. Starting number, we'll have our multiplier raised. We haven't done any halving yet, so raised to the x power. So let's just write these more formally in function notation. Y equals 2 times 3 to the x. Y equals 100 times half to the x. And this brings us to a good place to start generalizing. One basic form for an exponential function could be written in the form y equals our starting number, I'm going to call a, just based on common notation used in math textbooks and math websites. Our multiplier is called b, and that b represents what we'll ultimately call a base. It's the base of the exponential expression. Remember, 3 is a base, x is an exponent, and all of this has to do with powers. And then raised to the x power. In this case, where that's just a plain old x, we have a fact that a, this number right here, our starting number, is the y-intercept. Another way to say that is there's a point on the graph with coordinates 0 and a. And notice how that was true in both of these tables, 0, 2, 0, 100. So that's our basic setup when this is just a plain old x, no addition, no subtraction. And in that case, our starting number is the y-intercept. What we saw on our other page with equations that do have like an addition or a subtraction is very similar. So we'll just call this an alternate way. It might be a times b to the x minus something. I'm just going to put that as h. H will become a standard letter as we'll formalize things later in the course for starting, let's say shifting our starting number to a new location. So instead of starting at 0, we're shifting 5 spaces to 5. And we'll just use H for that. In this case, A is not the y-intercept, but there will be a point with coordinates H, comma A. So we're going to essentially think of the y-intercept as getting shifted sideways to this new point when we see a minus sign or a plus sign here. Notice how the math works. If I take that H and plug it into here, this quantity becomes 0. And that is identical to what happens if I take this 0 and plug it into here. The base to the 0 power is 1, and we're left with A. If we plug in H, we have a 0. The base to the 0 power is 1, and we're left with A. So think of this alternate form as the way of shifting our equation to be equivalent when we don't have the y-intercept. In that way, this version is kind of like point-slope form for lines, and this version is kind of like slope-intercept form for lines. Point was, we have different ways to do it. All right, one last challenge problem here. Here is a problem. We are asked to find the expression, ultimately the equation. And my first question is this thing even exponential? If it is exponential, we're going to use the top number as our starting number. There's no question there. But what is the multiplier? And then once we know the starting number and multiplier, we can write an equation. So let's start with this first question. Is it exponential? We're not going to get fancy here. We're just going to think of it simple. Is there one consistent number that multiplies down this table to generate these new values? And if we take out a calculator, I don't have one handy, so I'll just do the math on the side. But if we take out a calculator, we're basically asking 4.1 times what is 4.51? And I can find that value by dividing. Take the lower of the values, divide the upper. By lower, I mean like lower on the page, and divide the one before it. And if you punch that into a calculator, what you'll end up getting is the number that you multiply. In this case, that would be 1.1. Now, that doesn't mean this is exponential. It just means that's the multiplication relationship between these two numbers. For this to be an exponential pattern, we would need to use that same multiplier to go from row to row to row. So let's check it in just the same way. Take your third entry, 4.961, divide it by your second entry. And if that is equal to 1.1, it's starting to look like an exponential function. If that's not 1.1, this is not an exponential pattern because it doesn't use a constant multiplier. In this case, though, it is 1.1. And just for fun, we'll check this last one too. The weird thing about math is, in theory, you'd have to check all of them. But we're kind of going to rely on, if we see a consistent pattern 3 times, it's probably pretty reliable. Take this number, divide it by its preceding value. That happens to also be 1.1. So we're going to say that, is this exponential? Yes. It has a constant multiplier. Remember how linear had a constant adding value. Exponentials have a constant multiplier, and the multiplier is 1.1. All right, so I think we're ready to write our equation. I'm going to use the same format. The top row is going to give me my starting number. That's the number I would begin my process with. And then I'm going to multiply repeatedly by 1.1. But since we're beginning on row 3, I don't need to do all of the multiplications. 3 of them apparently have already been done to be starting here. So it'll be x minus 3. So we'll write our equation then as y equals 4.1 times 1.1 to the x minus 3.